Hey, it's a great pleasure to have David Kolchmeyer here from Harvard today to tell us about dynamical end-of-the-world branes and JT gravity. So go ahead, David, whenever you're ready.
Okay, thanks. Yeah, so thanks very much for the opportunity to speak here today about dynamical end-of-the-world branes and JT gravity. So this is going to be based off of some work I did with Ping Gao and Daniel Jafferis based on this paper. It came out earlier this year. So I guess our discussions about dynamical end-of-the-world branes and JT gravity started roughly after these two papers came out on replica wormholes. And the East Coast paper and the West Coast paper. And the basic message of these papers is that replica wormhole saddles and the Euclidean path integral can allow one to compute a unitary page curve for the radiation of an evaporating black hole. And in particular, this question was studied in toy models such as JT gravity with conformal matter and JT gravity with end-of-the-world branes. So for the time being, let's consider JT gravity with conformal matter. So here I've presented the double trumpet Euclidean wormhole of JT gravity. B is the length of the geodesic that goes around this double trumpet. And if I don't couple the two asymptotic ADS boundaries, then this path integral does not have a saddle. So in order to have a saddle, one has to have some sort of coupling between the two boundaries. And one way to do this is to couple the two boundaries to a shared bath system. And the idea is that the bath induces a coupling between the two boundaries, and then you can have a saddle. And so the argument of these papers is that we expect there to be a saddle in this case, and it would contribute to, in this case, the second Renyi entropy of Hawking radiation. So this is nice. The saddle point approximation is nice, but ideally we would like to be able to go beyond the saddle point approximation. And so it turns out that in this simple model of JT gravity and conformal matter, we can at least in principle do this. And what we find is that this path integral actually diverges because the matter path integral on the double trumpet diverges when B gets very small, diverges exponentially. So a naive person might say that the saddle point approximation is a horrible approximation to the correct answer because the correct answer is infinity, but we know better. And I think a better interpretation is that this is just a UV divergence in the effective field theory of JT gravity plus matter. And this just shows that the effective field theory is breaking down. So what we would ideally like to do in this situation is to regulate the UV divergence and express physical quantities in terms of renormalized parameters. And so this is something that we would like to be able to do in JT gravity with conformal matter, but we have not been able to do yet. On the other hand, we have been able to do this in a simpler model of JT gravity with dynamical end-of-the-world branes. And so that's going to be mostly what I'm going to tell you about today. So when I say JT gravity with dynamical end-of-the-world branes, what do I mean? So what I mean is that in the Euclidean path integral, we allow the end-of-the-world branes to run in loops, and we sum over multiple end-of-the-world brane boundaries in the Euclidean path integral. And this is a very natural thing to do. Another thing that's worth mentioning is that the West Coast replica wormhole paper explicitly studied the black hole information problem in the context of JT gravity with end-of-the-world branes. And so a natural question to ask then is what happens to this problem or what happens to this story when I make the end-of-the-world branes dynamical? So with this motivation out of the way, here's the plan for the talk. So first, I'm going to quantize JT gravity with end-of-the-world branes and Lorentz signature. So that'll just introduce the basic physics of these branes. Then I'll use that to explain how we would sum over loops of end-of-the-world branes in the Euclidean path integral. And then I'll point out where the divergences arise and show how some standard effective field theory logic can cure these divergences. And then after that, I'll discuss how the renormalization procedure we use also has a manifestation in the matrix model dual to this theory. And then at the end, I'll comment on how dynamical end-of-the-world branes impact the information problem in this model. Okay, so I'll just start with the basic Laurentian quantization of JT gravity canonically quantized on a spatial interval. So here we have one asymptotic ADS boundary and one end-of-the-world brane boundary condition on our spatial slice. So here's the action of JT gravity with the end-of-the-world brane. The action on the end-of-the-world brane is just that of a massive world line particle with mass mu. So on the ADS boundary, we're going to choose Dirichlet boundary conditions for the dilaton and the metric, as shown. And on the end of the world brane boundary, we choose Neumann boundary conditions, where we fix the extrinsic curvature to be 0. We fix the normal derivative of the dilaton to be mu. And then epsilon goes to 0 is just taking the ADS limit. So finding solutions to the equations of motion isn't too hard. We can just start with the more familiar two-sided black hole geometries, and then just put an end of the world brane somewhere in the space-time. So it's convenient to represent solutions as a cutout of global ADS2. So here I've just specified the metric of global ADS2. And in a particular reference frame, the profile of the dilaton looks something like this, where phi h is the horizon value of the dilaton.
Sorry, I have a quick question.
Sure.
Yeah. Could you just comment on your on the choice of boundary conditions at the end of the world brane? Is that the only option, or what are the sort of consistent things you could have done based on the variational principle?
Right. Yeah, that's a good point. So I guess well, yeah, so I mentioned that we have like Dirichlet boundary conditions here, and these are like Neumann boundary conditions. And so you have like a Dirichlet or Neumann boundary condition. So yeah, so I mean, there are different options. For example, we could, so another example could have been like fixing the dilaton and fixing the normal derivative of the dilaton, or fixing the metric, or fixing the extrinsic curvature. Yeah, so there are different choices that could be made. And I've only chosen one particular choice here.
Is there some, like, I mean, once you get to quantizing things and having loops of these things, I mean, would it be natural to sort of sum over the possible boundary conditions, or is it consistent to just choose one, or should we definitely just choose one? Or
well, yeah, that's a good question. I mean, maybe a priori, I'm not sure if I can give a good answer to that, but the way I like to think of these branes is, well, sort of analogous to like world line particles, except the space-time simply ends on the world line particle. That's how I think of it. Another way I like to think of it is that it's like having like a brane, it's like having a quantum mechanical system that lives on a brane. And so mu is simply like imagine having some arbitrary quantum mechanics that you want to put on the brane, then mu would represent, mu could run over the different energy levels of that quantum mechanical system. So I think this is like a natural choice. But yeah, I mean, the procedure that I'm about to talk about in terms of summing over arbitrary numbers of boundaries could be implemented with different kinds of boundary conditions too. I'm just not sure what the answer would be in those cases.
okay, sure.
But yeah, okay, yeah, thanks. So, good. So the space of time-like geodesics, which could represent the possible locations of the end of the world brane, is topologically that of a disk. So here I'll let R and theta parameterize the unit disk, just polar coordinates parameterizing the unit disk. And then this is the formula for a time-like geodesic given R and theta. And then there's this constraint from the boundary condition that basically fixes the location of the end of the world brane up to the boost isometry that leaves the dilaton profile invariant. So with that in mind, here's a picture of what a solution might look like. So the ADS boundary is out here. These are horizons, and here's the end of the world brane. And so these horizontal lines here are geodesics that end at the end of the on the end of the world brane at 90 degrees. Basically, they just represent a convenient foliation of the space-time into Cauchy slices. And the key point is that when mu is positive, the end of the world brane is always going to be behind the horizon. And then on the other hand, when mu is negative, the end of the world brane comes in front of the horizon. That's just a feature of these classical solutions. So here what I've described are the positive energy solutions that one can get. It turns out that there are also negative energy solutions. So for these, we can take the dilaton to have this profile where alpha is a parameter that just labels different dilaton solutions. And then this is a constraint on the solution. And so here's a picture. And one thing to keep in mind is that the negative energy solutions are only possible when mu is negative. That would follow from here or from the boundary condition. Okay, so having discussed the space of solutions, now I'll just tell you what happens if you, say, do an ADM decomposition of the metric or of the action and choose a gauge such that constant time slices are geodesics orthogonal to the end of the world brane. That's the gauge I showed you. So it turns out that after doing all the gauge fixing, just at the classical level, one ends up with a two-dimensional phase space, and it's parameterized by a renormalized geodesic length of the Cauchy slice, which I call W, and its conjugate momentum, which I call P. And the renormalized length is defined in terms of the bare length, like this. So you just subtract off this piece. That would be infinity in the ADS limit. Okay, good. So you get this two-dimensional phase space, and this is the Hamiltonian. It's very simple. So basically, it's just that of a scattering problem in quantum mechanics. Here I've drawn the potential for positive and negative values of mu. And again, only when mu is negative can you have negative energy solutions. And when you quantize, these will become bound states. Okay, so now for the rest of the talk, I'm going to focus on the case where mu is greater than -1/2. -1/2 is the threshold for having bound states. So we're going to focus on the case where there are scattering states only. So I'm going to now diagonalize the Hamiltonian with an energy eigenbasis. I'll use a quantum number called S. It's called S because it represents entropy above extremality of the black hole. And the energy is quadratic in S. And so I'll just normalize these eigenstates in this canonical way. And the wave function in the W basis of an energy eigenstate is given by this function over here. This W is called the Whittaker W function. It's an analog of the Bessel K function. And so once we've diagonalized the Hamiltonian, we can simply compute the Euclidean propagator, which is this quantity. And we compute it simply by inserting a complete set of states, of eigenstates. And then it turns out that one can use a non-trivial integral identity that one can just look up. And the answer for the Euclidean propagator ends up taking this form. And here, to get this answer, it was important that I used that mu is greater than -1/2, because that is what is needed for this integral to converge for large B.
I'm sorry, I've forgotten what the variable little w represents.
Oh, sure, no problem. So basically, W represents, say, the length of any of these geodesics here.
Okay.
So it's just the length of the Cauchy slice.
Got it.
Yeah, thanks. Yeah, so now we're just computing the Euclidean propagator from like one Cauchy slice to another. And it ends up taking this form. So this red line over here is something that basically appeared in the literature before. It goes by the name of the boundary particle propagator in this formalism, this boundary particle formalism of JT gravity that was developed in these papers. So on the next slide, I'm going to tell you, I guess, physically what this red line is computing.
Sorry, can I ask a question about this? About that? So,
yeah, sure.
Is it right to say that if you took W1 to be 0, then this would be computing the Hartle-Hawking wave function?
Not quite. So actually, W runs from -infinity to infinity, because this is like a renormalized geodesic length. So we can never take the length. We can never take the length to be 0 because we're working with like a renormalized geodesic length. Yeah. So so the formula for the Hartle-Hawking wave function would be a little different. Yeah.
I see. But can it be derived from the inner product between the W and the S states that you wrote down? So in JT gravity without end of the world branes, I think it can be. You just integrate against the density. But I guess I'm not sure what the density is in your case.
But doesn't having an end of the world brane mean you're sort of in a different sector from the Hartle-Hawking, the one that the Hartle-Hawking vacuum would be in?
There would still be an analogous state, right? Which would look like a half disk with some length W between an end of the, exactly. So I guess,
okay.
I'm just asking how to compute this this wave function given your formulas.
That's a good question. So I don't think that can be computed directly from what I have here because, yeah, as was mentioned here, what we can compute is something like this. So this is what this formula computes. So to me, it's not directly clear how you would get a formula for this from this. So there was a formula for this given in this West Coast replica wormholes paper. And I think the one way to justify it is to, well, for example, you could, compute like you could imagine computing, for example, I don't know, the expectation value as a function of time of like the W operator in this state in like the semi-classical limit and check that, it kind of evolves according to like the semi-classical or classical intuition, like the scattering problem that I mentioned. So that's one way you could kind of verify that the Hartle-Hawking state is correct. Yeah, but I'm not sure how to exactly derive that from this formula here. Though I think that the formula that they gave for the Hartle-Hawking state in their paper is correct.
Okay, thanks.
Yeah. Great, thanks for the question. Good, so now I'll just say a few words about this boundary particle propagator and what exactly is being computed here. So here I have the hyperbolic disk, hyperbolic Euclidean disk. This red line is a geodesic that goes through the center. And so I imagine choosing 2 points that are separated by a distance b, and then I'll consider orthogonal geodesics to the endpoints here that have normalized geodesic lengths W1 and W2. And the idea is that basically this boundary particle propagator is computing a sum over trajectories that start here and end here. And so I represented that by this squiggly orange line. And so what this means is that, so for example, let's suppose that I take W1, W2, set those 2 lengths to be the same, and then identify those 2 geodesics. Then the geometry in here just becomes that of the trumpet. And then summing over, these orange boundaries just corresponds to summing over the wiggles of the trumpet. So basically the conclusion is that if I take the Euclidean path integral and just compute this integral over here, or equivalently just compute the trace of e to the minus beta h, or the partition function of this system I just quantized, then that's going to be equal to JT gravity with a trumpet. And then at the geodesic boundary of that trumpet, we have an end of the world brane. Good. So here, Z trumpet is the formula for the trumpet that was given by Sod, Schenker, and Stanford. And the idea is that you just integrate over the length of that geodesic with this particular measure, which I derived from here. And then that gives you the answer with one ADS boundary and one end of the world brane boundary. You might already notice that this is divergent as B goes to 0, but I'll come back to that later. Okay, so this is how we compute the path integral with one ADS boundary and one end of the world brane boundary. So now we can just generalize this to include more end of the world brane boundaries. So the calculation that we're interested in is a calculation where there are k species of end of the world branes. And I'm going to suppose that this genus suppression parameter, e to the s naught, is very large so that we don't have to consider handles. And I'm going to assume that k is on the order of e to the s naught. So as mentioned before, here's the measure for the end of the world brane. So now what we want to do is we want to compute the partition function of a black hole in this theory. So it gets a contribution from the disk of pure JT gravity, that's this term. This next term is the trumpet I computed on the previous slide. So this is with one end of the world brane and a factor of k for k species. And now each term in this sum will compute the path integral with one ADS boundary and n end of the world brane boundaries. So to do that, I just start with the Wahl-Peterson volume with n+1 boundaries. And n of those boundaries will be glued with end of the world branes. So here I integrate with this end of the world brane measure. And then the last boundary just gets glued in with the trumpet to give you the asymptotically ADS boundary. So we just have to sum over all this. So To explicitly do this, we use a method that was used in previous work to sum over arbitrary numbers of conical defects in JT-gravity. And I'm not going to review the details of this calculation because it's a little complicated. And also, again, this isn't a new thing that we invented. So it starts with this convenient formula for the Wahl-Petersen volume, which is given in terms of this function u of x, which is defined implicitly by this equation. And so it's convenient to actually take the end of the world brane measure and integrate it against this Bessel function J0 to define a new function, which I'll call f of u. And the idea is that the answer for the black hole partition function only depends on the end of the world brane measure through f of u. So f of u encodes the data of the end of the world brane. And so we can write our answer for z of beta in terms of f of u. And this is what the answer is. So to do this, I need to define a new function called xi of x. It's defined implicitly by this equation over here. So here f makes its appearance. And then I just integrate this function from 0 to infinity, and that's the partition function. So one thing is that if I take k to 0, then this is just another way of expressing the disk path integral of pure JT gravity. So if it happens to be the case that this function xi of x is not single valued, as x goes from 0 to infinity, which could be the case because it was defined implicitly, then it turns out that the computation can't be trusted. And indeed, this answer wouldn't even make sense anyway. So we have to make sure that we're always in this regime. And once I have the partition function here, I can do an inverse Laplace transform to get the density of states. And the key point is that the 0-point energy of the spectrum depends on the value of xi at 0. Okay, so now I'll come back and talk about the divergence. So the integral that defines f of u is log divergent as b goes to 0, as you could see here. On the other hand, f prime of u converges. So basically, I want to just use like a standard effective field theory approach. So you could imagine, having like some loop Feynman diagram that's divergent. So in that case, we take derivatives with respect to the external momenta enough times until we get a convergent answer, and then we have the answer in terms of a finite number of integration constants, which can be affected by counter terms. So I want to do the exact same thing here. So f prime of u converges. And this just means that we should imagine that we know f of u up to an overall constant that just shifts its value. So what does this overall constant mean? So again, it was shown in these earlier papers that if I sum over cusps in the path integral or conical defects with deficit angle 2 pi, this just has the effect of changing f of u by a constant. So basically, the idea is that summing over n world branes by itself isn't a nice thing to do. Instead, we have to sum over n of the world branes and cusps. And the cusps will have an amplitude that will cancel the UV divergence of the end of the world brane. And so what this means is that we have f of u up to an overall constant, and we just think of this as parameterizing our ignorance of the UV physics. So going forward, I'm going to fix this constant so that f of 0 is just 0. And the reason why I do this is because it implies that if I take the limit where the end of the world branes become infinitely massive, then in the IR, I just get pure JT gravity again. And so it's a nice picture I like to have. When the end of the world branes are very massive, then the physics there sort of decouples and you just get pure JT gravity again. For a different value of this counter term, you would get pure JT gravity with cusps in the IR. So I just won't consider that case. Okay, so with that out of the way, I guess I'll just show some plots over here. So again, this is the equation that determines xi of x, and xi of 0 determines the 0-point spectrum, the 0-point energy of the spectrum. So here I've plotted the function f. And maybe I should also plot this first function over here involving the Bessel function. Basically, it just starts here at 0 and grows very, very quickly. So the idea is that as I increase k from 0, the 0-point energy of the spectrum starts at 0, but eventually, once k reaches some critical value, the 0-point energy will start to shift to the right. And that's what's shown in this plot over here. So on the x-axis is just plotting k, and then on the y-axis is plotting xi of 0. And so at this critical point over here, the 0 point energy starts to shift to the right. Okay, so let's just assume that k is below this critical value of k. So I can write a simple formula for the density of states. It's just a sum of the density of states of pure JT gravity, the disk density of states of pure JT gravity, plus this correction, which I'll call rho sub k. And so here's a formula for rho sub k. You might notice that this formula is negative, manifestly negative. So that means that as I take k to be large enough, eventually the total density of states rho will have negativity. But the point at which this happens is precisely the value k equals kc. So that just means that we don't, this equation won't apply past that point. And so this is something that was similarly observed in a paper by Johnson and Rosso of last year, where again, they considered deformed GT gravity theories, and they considered cases where a naive calculation would suggest that the density of states had negativity, but a correct calculation would just indicate that the 0 point energy of the spectrum has changed. Okay, so I mentioned earlier that this gravity calculation of summing over all the end of the world branes can break down in a certain regime of parameters. And so I just want to show that over here. So on the x-axis, I plot k. And on the y-axis, I just plot the value of a constant additive term that could shift the value of f. And so again, in this talk, I'm focusing on this regime over here where we're just on this line. And this is the critical value of k I mentioned earlier. Yeah, so for these values here, the calculation I mentioned goes through. Whereas here, if we try to adjust the counter term to be in this region, one can't sum over all the end of the world branes. So if there's time at the end of the talk, it turns out that using some information about the dual matrix model, one can make an argument for what could possibly happen in this disallowed region. But I can come back to that later if there's extra time. Okay.
A question?
Oh, sure, yeah.
Yeah, is this critical value of k, can I understand the physics of that as being related in some way to, or is it similar to in the simple model of Maralf and Maxfield, they had some kind of critical value for k, as I recall. I'm not quite remembering what the implication was, but it had some fundamental interpretation in terms of Hilbert space dimensions.
Well, yeah. I think there was something very important. Yeah, so there's something important that happens there when the number of end of the world branes basically. Right. So what? Yeah. So I think the idea there is that if you have too many end of the world branes, then they can't all be orthogonal in the Hilbert space. So I think maybe their critical value is when the number of end of the world branes saturates the Hilbert space. In other words, you can't take them to be orthogonal states anymore. So I wouldn't exactly say that the critical k here corresponds to that, but we'll see something similar. We'll see something related to that.
Okay.
Yeah. Okay.
Good. Thanks.
Yes. Okay. Yep. Thanks. Good. So yeah. So the next thing I wanted to mention was what happens, say, to the effective action for the metric and the dilaton if you integrate out the end of the world branes. So the idea is that after integrating out the branes, we want to look for some effective action for the metric and the dilaton whose path integral on the disk reproduces z of beta. So I claim that the effective action is this. I just wrote the bulk term. The boundary term is the same. Basically, I just claim that you get this additional potential for the dilaton after integrating out the end of the world branes. I restored the factors of G Newton just to illustrate that G Newton is not appearing as an overall prefactor for the action. And so here's the formula for this extra potential, which I call U of k. And in the spirit of effective field theory, I'm going to expand it in a large mu expansion or a large mass expansion, because mu is like the scale of the physics that we're integrating out. So this is what you get. Basically, it's e to the minus 2 pi times the dilaton. And then here you just have polynomials in the dilaton. So now I have to convince you that this is the correct effective action, the correct potential. So to do this, I'm going to refer to this earlier paper by Whitten, where he wrote down a formula for the disk density of states that's associated with potentials of the following form. So here he considered a linear combination of exponentials where the exponent, this parameter alpha, goes between pi and 2 pi. And also these coefficients epsilon have to be chosen such that u of 0 is 0. So if this is obeyed, then he actually provided a formula that looks like the change of the density of states from the disk density of states in pure JT gravity is actually linear in U, provided that these conditions are met. So basically, each term in the large mu expansion I showed on the previous slide takes the form that Whitten considered for limiting values of the parameters. So you have to take derivatives with respect to alpha and set alpha equals to 2 pi. But basically, I just claim that each term in the large mu expansion is what, takes the form of what Whitten considered. And so I can just compute the density of states using his formula. And the answer matches what I called rho sub k earlier in the talk, order by order and 1 over mu. So basically, it just matches the expectations from the calculation we did, order by order and 1 over mu. So in this way, I claim that's what the effective action is. Okay, so now once we have this effective action, we can do a semi-classical analysis with it. But I emphasize that we can only get an intuitive understanding and not a quantitative understanding, because we don't really have parametric control over a semi-classical approximation, because 8 pi g Newton doesn't appear as an overall prefactor. But still, let's see how much mileage we can get. So the zero temperature entropy of a black hole in this case is given by S naught plus phi star over 4g, where phi star is just the largest root of the potential. So this is the potential from pure JT gravity and then the correction due to the end of the world branes, and we just look for the largest root. And phi star would just be the value of phi on the horizon of that zero temperature black hole. Okay, so the zero temperature entropy then, okay, so we can just do this. And we find that when k is asymptotically large, the zero temperature entropy goes as log of k. And the thing that's significant is that it goes as log of k with a prefactor of 1 and not some other prefactor. And so as a result, I want to claim that that the zero temperature entropy, for asymptotically large values of k, is counting the number of end of the world branes that have been integrated out. So I think this is a nice picture because we have this picture where we have end of the world branes, we can integrate them out, and then the number of branes is still present in the semi-classical entropy formula, which kind of makes sense. So you could say that this is a model of induced gravity for that reason. Okay, so here, so on the previous slide, I used the semi-classical analysis to say what the black hole entropy is, but we actually have computed the full black hole partition function, so I can just plot, the exact numerical answer. So here, I've just plotted the entropy of the black hole from z of beta for different values of the temperature. And on the x-axis here, it's just the number of the world branes, and on the y-axis is the entropy. And so the idea is that as I increase k from 0, eventually there will come some point where k saturates the entropy, and beyond that point, the entropy of the black hole will simply increase to take into account the number of species of branes that have been integrated out. So I would say perhaps an analogy of this critical value of k that was maybe observed by Marolf and Maxfield, I'd say the analogy would simply be where k here, or where log k here meets the entropy of the black hole. So this is where something interesting happens. Yep. At these places. But the interpretation of what happens past that critical point is going to be different in my story here versus their story. And I'll come back to that. Right. Basically here, I'm saying that the end of the world brane states will continue to be orthogonal, and the entropy is just updated to reflect the new number of states, the new number of species in the theory. Okay. Good. Okay, so now a few words about the dual matrix model. So, right, so Saj, Shanker, and Stanford showed in 2019 that pure JT gravity is dual to a double-scaled matrix model. And in particular, the Euclidean path integral of JT gravity with n ADS boundaries is given by this correlator over here. So it's just an expectation value in the matrix model ensemble of a product of partition functions where H is the matrix. So I claim that this formula that I've written here will compute the Euclidean path integral with n ADS boundaries and k species of end of the world branes with mass mu summed over all the species of end of the world branes. Okay, so basically, if you want to verify this claim, all you have to do is take this exponential and just expand it. And so you just get a bunch of traces. And the formula for a correlator with any number of traces was given to us by Saj, Shanker, and Stanford. And so all you have to do is just plug in, the function that I've provided here into their formula and simplify it. And you'll see that this just reproduces the sum with an arbitrary number of end of the world brane boundaries. I also divide by the expectation value of this exponential over here. That's just serves to cancel out unwanted diagrams so that the remaining diagrams that we have are just diagrams where all the end of the world branes are connected to an ADS boundary through the bulk. So one thing to note is that this integral here is divergent for small b goes to 0. But that's okay because if you take the derivative with respect to h, then it is convergent. So the divergence doesn't depend on the Hamiltonian h. So for that reason, it can actually just come out of the correlator over here on the top and bottom, and it cancels. So with that in mind, this term here in the exponential just becomes something that gets added to the potential of the matrix model. And so once you subtract this infinite constant, or you take the derivative and then do the integral and then integrate that, what you find is that the change of the potential of the matrix model delta V is given by this formula over here. Okay, so now we'll ask what happens when we take the SSS matrix model and then simply add this delta V to the potential. So one thing that I want to point out that's a little curious is that if I take delta V and compute the force, so minus delta V prime of the energy, this actually just becomes a sum over poles. And the force is always pointing to the left. And something that's curious about this formula is that, well, while of course it makes sense for mu greater than -1/2, it also makes sense for mu less than -1/2. So for this whole talk, I was considering the case where mu is greater than -1/2, because that's where I had this picture. That's where the picture of the Euclidean path integral made sense. But here, once we talk about the matrix model, it seems like there's a way to perhaps think about what the Euclidean path integral might mean or what the theory might mean when mu is less than -1/2, because it just adds extra terms to the potential, basically. So I think this is curious and worth coming back to, but I'm not, I haven't pursued this further. But it's still, yes,
just
please.
Going back to your previous formula, is there is it possible there's a somehow a more basic way to write this? But I guess I was envisioning starting with a matrix model and actually adding some, I don't know, vector or something that would represent a boundary of the.
Oh, sure. So that's what I have here.
Oh, okay.
These are the vectors.
Okay, great.
Yeah. So right. So one can do something similar to what's been done before. Yeah. So indeed. So these other papers by Rolf Maxfield and the West Coast paper, they wanted to think of these end of the world branes, as states in the Hilbert space, and from the perspective of the disorder average theory, we can basically consider these complex bosons here. So I labels an end of the world brane, and A is a component of a vector. And so in addition to averaging over a random matrix, we also have a random vector. And the variance for the Gaussian measure for these vectors here, this is in accord with this West Coast replica wormholes paper. Yeah, so basically we're getting the same the correlation functions of these complex bosons end up being the same. And so what I wanted to say about this is that if you integrate out these vectors, then you get a change of the potential delta V that exactly equals what I computed on the previous slide for delta V. So the point I want to emphasize is that considering dynamical end of the world branes is very natural, both from the gravity point of view, but also from the matrix model point of view, because this interpretation in terms of vectors isn't new. But now all I'm saying is that just integrate the vectors out. It gives you a change to the potential of the matrix model, which corresponds to the dynamical brane. So I think that's a nice picture. Okay, so now just a quick fact about matrix models. So the tree level density of states rho of E of a general Hermitian matrix model obeys the saddle point equation. So I'll write that equation first by defining the effective potential, which just says that the effective force on an eigenvalue at some energy E is the sum of the force from the matrix model potential plus the force on the eigenvalue from all of the other eigenvalues. So again, I'm using this picture where the eigenvalues are like charges that exert this Coulomb repulsive force against each other. And then the saddle point equation for the matrix model is simply that the effective potential is constant on the support of the density of states. Okay, so now we can simply consider this equation where I replace V with V plus delta V. And so what do we get? So here, this is the, so if we change the potential by delta V, then the change of the density of states, which I call rho of V, will just obey this equation over here. So here, V effective is the V effective in the original undeformed matrix model of Saad, Shanker, and Stanford. And all I'm saying is that if you just update that definition to include the contribution from delta E and the change of the density of states delta rho, then you just get this equation where these three terms sum up to 0. And the point is that these three terms are all well-defined and finite in the double scaling limit. And so we can use this to solve for delta rho. So actually, if we want to solve for the change of the density of states delta rho, we need to be given the support of rho plus delta rho of the final density of states. So once we're given that support, we can just solve this equation here. And the point is that if you take all the spectra that arise from the gravity calculation I did earlier for different values of the counter term, you'll get spectra that are supported on the half real line, E naught to infinity, and they all obey the above saddle point equation. So that's good because I claim that this is the dual. This is the matrix model dual. So one thing that's worth pointing out is that in usual matrix models, the endpoints of the spectrum are not free parameters. They're determined by this normalization condition. So here I should say, if I'm going to change the potential by delta V, then I'm not changing the number of eigenvalues. So we should have this normalization condition, just saying that the integral of delta rho is 0. But it turns out that for any value of E naught or for any value of the counter term I mentioned, we actually find that the specific formula for delta rho is not even normalizable. This is basically just a symptom of the fact that I'm computing all these quantities directly in the double scaling limit. So delta rho is the change of the density of states in the double scaling limit. So perhaps it's not surprising that some infinities are coming about, but I'll tell you how we think of this on this slide. So basically the conclusion is that the definition of the matrix model dual to the end of the world branes is not uniquely determined by the change in the potential delta V, even though naively that's what it might seem to be. So in particular, the 0 point energy of the spectrum E naught is determined by details of how the double scaling limit is taken. And these details can affect the number of eigenvalues that are available to fill in the well created by the potential. So maybe just to illustrate what I mean, let's suppose that I just consider some matrix model, where the potential is very simple. It just has this potential well, and the density of states or the spectrum will just fill, the eigenvalues will just fill this well, say up to here. So in the double scaled limit, the support of the spectrum goes from E naught to infinity. And the idea is that one could consider designing a new double scaling limit where the number of eigenvalues goes to infinity faster or slower than the previous double scaling limit in such a way to effectively change the number of eigenvalues that are filling the potential well. So for example, I could imagine, in this way, effectively decreasing the number of eigenvalues that fill the potential well down to here, and then the endpoint of the spectrum changes. So the point I want to make is that on the matrix model side, if we work in the double scaling limit, there's some ambiguity in the endpoint of the spectrum, and that's the only ambiguity. And so we want to see that as being dual to this counter term ambiguity that we saw on this gravity side. So somehow the UV physics of the gravity theory is supposed to be encoded in details of how the double scaling limit is taken, or at least this is the interpretation that we want to have. Okay, so I guess in my remaining 10 minutes, I'll comment on perhaps what all of this implies for the information paradox as it has been formulated in this model. So the West Coast replica wormhole paper formulated a version of the information problem in GT-gravity and end-of-the-world branes. And basically their problem went something like this. So let's consider a classical black hole solution with K species of end-of-the-world brane behind the horizon. So the semi-classical Bekenson-Hawking entropy of this solution is S naught plus phi h over 4g. And basically the information problem is that this entropy is seemingly unrelated to log K. So in other words, there seem to be perfectly good semi-classical configurations where the number of end-of-the-world brane species behind the horizon exceeds what is expected from the Bekenson-Hawking entropy formula. And so that's a problem. And to make that problem severe, they imagine coupling this system to a bath and creating a very highly entangled state that defies expectations, I guess. So for the case of non-dynamical branes, which is what they considered, they performed a calculation involving replica wormholes. And this implies that the end-of-the-world brane states are no longer orthogonal. So here the story is a little different. So here we consider dynamical end-of-the-world branes, and I argued that the black hole entropy includes the entropy of the end-of-the-world branes. So in other words, when K goes past this critical this critical point that I showed on that plot, so the entropy of the black hole, the entropy of the black hole is just increasing, and so it will always be large enough to account for K orthogonal end-of-the-world brane states that have been integrated out and affect the semi-classical action. And so I would say that this is another way, at least technically, how this information problem could be resolved. In particular, if you repeat the replica wormhole calculations with the dynamical end-of-the-world branes, basically you just use the new density of states that I showed, and the extra contribution of log K to the zero temperature entropy would imply that the replica wormhole saddle is never dominant. Okay, so now it seems like there are two different scenarios to consider. One with dynamical end-of-the-world branes and one without dynamical end-of-the-world branes. And so one question might be, which one is probably a better toy model for what happens in higher dimensions or more complicated theories? And I would say that the non-dynamical brane model is probably better for intuition about Hawking's original paradox. And that's just simply because in this case, we actually do get a page curve. Here with dynamical end-of-the-world branes, I'm not sure how to extract a clear page curve, at least with an understanding. I'm not sure how to extract a clear page curve because, as I increase K, I'm actually changing basically the field content of the theory. I'm changing the number of states that can run in loops. And we don't imagine that the field content of the theory is changing as the black hole evaporates. So in a sense, this is some alternate mechanism that would resolve this information problem, but maybe it just does so in some technical way. But with that said, I think it would be nice if one could formulate, I guess, some analogous information problem to this West Coast paper that cannot technically be resolved by dynamical end of the world branes. And so that's what I'm going to do now. So I'm going to basically just formulate a similar but slightly different problem and then pose some questions that I have about it. Okay, so let me refer to the Hilbert space I mentioned at the beginning of this talk as H sub mu. So that's just one asymptotic ADS boundary and one end of the world brane boundary. And this describes states of boundary gravitons. That's basically because the dynamics of JT gravity, comes from this fluctuating boundary. So in a paper from about over a year ago with Daniel Jafferis, we showed that these boundary gravitons should be thought of as bulk matter fields for the purposes of applying the quantum HRT formula. So, in the usual story, one wants to compute the entanglement entropy of the entanglement wedge. So you have to sum over the codimension 2 area of the quantum extremal surface, and you have to sum over the entropy of the bulk fields in the entanglement wedge. And so we just considered pure JT gravity in that example and showed that this bulk entropy should be the entropy of the boundary gravitons. Okay, so since we don't have matter in the bulk, I guess this is the only thing that could really contribute to that term. So with that in mind, let's do something similar to the West Coast paper and consider the following state in H mu with a Bath-Hilbert space as well. So this is a maximally entangled state, and I'll let I refer to an orthonormal basis of the Bath. And then psi I is a set of n orthonormal states that are localized within a microcanonical energy window. And I can take n to be arbitrarily large because the energy spectrum is a continuum. In particular, I can take n to be greater than e to the s, where s is the microcanonical entropy associated with this microcanonical energy window. And so because I can take n to be arbitrarily large, there is an information problem that's analogous to the one in the West Coast paper. So basically, instead of entangling many end of the world brane states with the Bath, I'm just considering the case where there's one end of the world brane state and I'm entangling boundary gravitons with the Bath. And I can, I can take n to be as large as I want. So that's the problem. Okay, so one thing that one might do is to do something similar to what this West Coast paper did. You can compute the von Neumann or Renyi entropies of the Bath reduced density matrix, which I'll call sigma, using the Euclidean gravitational path integral. And we know, from SSS that Euclidean path integral calculations in JT gravity are dual to matrix model calculations. So I'll give an example here. If I wanted to compute trace sigma to the n, basically I can just write out the answer in terms of the wave function of these states psi I in the energy basis and the density of states of the matrix model. And then when I take the matrix model expectation value, I just average over these density of states here. So this is something a little different than what this West Coast paper did, because they also took the states themselves to be like, end of the world brane states, which are selected from an ensemble. But here I'm not doing that. But I mean, that's okay. That's another thing. It's a perfectly valid calculation to do. Okay, so the point is we can use the matrix model to compute these Euclidean path integral calculations. And in a single instance of the matrix model, the spectrum is discrete. And so this just means that if you compute the Bath entropy, you get an answer that's consistent with the microcanonical entropy. So in other words, in any single instantiation of the matrix model, of course, I cannot take n to be arbitrarily large. And instead, what you'll find is that many of these continuum energy eigenstates are actually null. And so the words that we can say, are that due to non-perturbative effects, this many of the states in this continuous spectrum of energies are actually null. And so that's a way that you could resolve this problem in a very similar way to the West Coast paper. But with that said, there's still, I think, a question that should be answered. And that is, does the concept of an island make sense in this example? Usually when we talk about islands, we have a semi-classical setup of classical gravity and quantum matter. Here, I put the matter away. We only have gravity, so we better quantize it. But now that the metric is fluctuating, how do we think of an island? In particular, there's this close connection between replica wormholes and islands. And in this calculation, you still have replica wormholes. You still have wormholes here from this expectation value, but I'm not sure what an island means, I guess, in this sense, when the metric is quantized. So that's something I'm thinking about. And I'll just say one more thing now about this additional problem, and then I'll be done. Right, so again, this problem that I'm posing is that in Laurentian signature, the low energy theory, the low energy effective theory is predicting a continuum of orthogonal states, but of course, in any reasonable UV completion, the spectrum is discrete. So, of course, one way to resolve this problem is to do what I just said, but maybe another perspective one might want to take is that somehow we have to argue that the effective field theory is being applied outside of its regime of validity. So from the Laurentian perspective, the divergence in the number of states is an IR divergence. And this is because in this scattering problem, the potential for the normalized geodesic length W goes to 0 as W goes to infinity. So you can have a continuum of scattering states, and that's the infinity. But on the other hand, I also showed that the partition function computed in the Laurentian theory is actually equal to the Euclidean path integral on the trumpet. And there, the divergence is interpreted as a UV divergence. So it's tempting because once I can interpret this divergence of the number of states as a UV divergence, it seems like one can make an argument that the theory is being applied outside of its domain of validity. So this is just an idea I wanted to mention. I haven't been able to make this precise. I mean, so I already mentioned how we can regulate the UV divergence in the Euclidean path integral. So somehow we might want to take that as the definition of the regulated partition function. But still, the implications of this for the Laurentian physics are unclear. So like why, from the Laurentian perspective, why is the spectrum discrete? Okay, so I'll just say one more thing and then I'm done. So, I mentioned that there's this like UV or IR divergence. And something curious happens that one can see if one also includes conformal matter. So let me just quickly say what happens to the problem I mentioned at the beginning, this Laurentian quantization problem, when I include conformal matter or really just any matter in the bulk. So the Hilbert space with matter just becomes a direct sum of the Hilbert space I considered previously. The idea is that the parameter mu is changed to mu plus EI, where EI is the energy spectrum of the bulk matter theory, quantized just on ADS with the boundary ending on the end of the world brane. So in a sense, including bulk matter is very similar to just having many species of end of the world branes. Basically because from the perspective of the boundary graviton, all that matters in the bulk is the total energy in the bulk, whether that comes from matter or end of the world branes. And so now I want to imagine computing the trace over this Hilbert space of e to the minus beta h, but I'm going to insert a projector onto an eigenspace that corresponds to a fixed length of the geodesic Cauchy slice. And so intuitively, I want to count the number of matter states that can propagate on the geodesic Cauchy slice with renormalized length W. And here I put this e to the minus beta h just to suppress high energy states. So roughly, it's like we're counting the number of states below some energy, roughly, on a certain Cauchy slice. So intuitively, that's what this computation is. So we can actually compute this quantity using the Euclidean propagator that I mentioned at the beginning. So this is the Euclidean propagator again, where I set W1 equals to W2 equals W. So if I did not have Z CFT over here, then basically this is just the expression for the propagator I mentioned earlier. And so to include matter, I just have to insert the partition function of the CFT over here, which just takes that form. And so the point is that there are two important contributions that occur when B is very small. So when B is small, the partition function of the CFT diverges like this. It diverges exponentially in B. On the other hand, there's also this extra term, which goes to 0 exponentially quickly. It just comes from taking the small b limit over here and over here. So the point is that when b is very small, whether or not you get a divergence depends on the value of the central charge of the CFT, and more importantly, the length, the renormalized geodesic length of the Cauchy surface, of the Cauchy slice that we're considering. So the point is that when the renormalized geodesic length is sufficiently large, the path integral diverges. So, so it's curious, again, that the number of states roughly on the Cauchy slice seems to diverge when the length is greater than some certain value. So again, it's tempting to think that maybe we've identified some value of this length, or maybe that we can say that the theory is breaking down or it's being applied outside of its regime of validity. But this is something I'm investigating further. So with that, I'll just conclude and summarize. So I guess the main takeaway message is that dynamical end-of-the-world branes are natural to consider, both from the gravitational path integral and from the dual matrix model perspective. And so when integrating over these branes, you get divergences in the path integral, and they can be addressed using standard effective field theory logic, where the IR parameter is the 0-point energy of the spectrum. Furthermore, dynamical branes contribute to the black hole entropy when you integrate them out. And so this can be seen as resolving a potential information problem. But also, as I mentioned, one can pose an analogous but different information problem involving entanglement with boundary gravitons that is not resolved by dynamical end-of-the-world branes. And I identified some further questions in the setup that I think are interesting and should be answered. Okay, so I guess I'm out of time now, so I'll just say thank you.
Questions for David?
Maybe just a general question about, about the setup. So you might think it would be required somehow to actually integrate or treat them as dynamical as you did. Is
Sure.
it? I mean, is it clear that it's sort of even consistent to introduce end-of-the-world branes in a gravitational theory without having them be dynamical? If they're not like asymptotic, I mean, I guess we have asymptotic boundary, or we have sort of asymptotic boundaries, which we think don't have to be dynamical, but with what we'd call an end-of-the-world brane, it's almost part of the I would think maybe it's almost part of the definition that it's a dynamical object.
Right. Yeah, it is part of the, yes. Yeah, I mean, I agree with that statement. Now, when it comes to these very simple theories of gravity, you can always take the definition to be the definition of a disorder average theory. So you could always define it like that. So in a sense, you can always avoid inconsistency just by saying, this is supposed to be dual to a particular disorder average theory. And so I think in the West Coast replica wormhole paper, they specified what that theory is. So in that way, technically, sure, it can be consistent without integrating over the branes. But I guess one point I wanted to make is that if you have this interpretation of branes as vectors, it's very natural to ask, if you integrate out the vectors, how does that change the potential of the matrix model? And that's, in a way, that's consistent with density. So, it's a very natural thing to consider. I'm not sure of any sharp argument against, a sharp argument against non-dynamical branes. But yeah, so.
Okay. Yeah. I just wanted to make sure that I understood the dual of your system. So could you go back to where you wrote down the matrix model?
Yeah, absolutely.
I think I was confused about one point in particular. So
yeah,
for the bulk branes, you integrate them out, and that modifies the potential, right? And those effects come from branes that kind of float in the bulk, and you can integrate over them as loops, right? And
exactly.
In your model, you can also have branes that connect asymptotic boundaries, like that are associated with boundary segments, right?
Yeah, you can do that. Yeah, so here, it's like, yeah, it's kind of like the same as what's been said before, that you think of this as being like an inner product of
Exactly.
psi
Yeah.
I, psi
And so
j.
I guess what I was confused about was in the matrix model that's written on the screen now,
Mm-hmm.
I see the vectors, like the random vectors in the Hilbert space, which are these psi variables. But
Yes.
why is the matrix potential still the one of Sachenker-Stanford and not your deformed potential?
That's a good question. Well, the idea is that, so when I want to compute this diagram, which is this, I have to do the Wick contractions over these over these complex bosons, and then you also get a contribution from like the determinant of this. And so the determinant of this will change the potential to make it the potential corresponding to the dynamical branes. And then the Wick contractions of the complex bosons give you the like the factors here that would basically correspond to, defining the Hartle-Hawking state.
Okay, I see.
Yeah.
So the integration of the psi variables actually gives you both effects. Okay.
Yeah, so you get both effects. Yeah.
Okay, got it. Thanks. So it's just like Maroff and Maxfield, where they have some non-dynamical end of the world branes, but then they can integrate over them, and during the integral, you both modify the bulk coupling as well as sum over the random vectors. That's
right. Yeah. So doing that integral should take into all the effects of that's
okay.
That's right. Yeah. Mm-hmm.
Thanks.
Mm-hmm. Mm-hmm.
Is there a way to, you mentioned that these possible null states that would end up making your spectrum discrete. I'm wondering if there's a way to kind of see that explicitly. Is there a calculation or something that?
Well, let's see. So how do we well, somehow the logic was supposed to be that any calculation done that's averaging over single instances of the matrix model should be, I guess, consistent with an expectation of having a discrete spectrum, because you're just averaging an answer over different theories with discrete spectra.
Mm-hmm.
So on the matrix model side, I mean, that's what's happening. And any calculation of this kind has a dual as a Euclidean path integral. So I don't think I have anything new just in regards to that, beyond what Maroff and Maxfield already said. So I think the whole story of baby universes and alpha sectors just completely goes through here, where each alpha sector is like an instance of the matrix model. But the thing I'm really curious about, though, is what this means for like Laurentian physics. Well, I mean, we have this, this alpha parameter story, but I also want to see if it could be related to either islands, even though I'm not sure exactly what an island means in this example, or this other curious fact that a UV divergence in the Euclidean theory is an IR divergence in the Laurentian theory. So somehow I want to have an additional interpretation of this, but so far I don't have one. So I guess I have to say the words that have already been said about alpha parameters. Yeah.
Okay, looks like there's no more questions. So let's thank David again.
Okay, thanks.
Thanks for the talk.
Oh, sure. Thanks. Thanks for the questions.
David. Nice, interesting talk.